Okay, welcome to tutorial 3 where we're going to be looking at voltage dividers. It's a very simple circuit. We have a pull-up resistor and a pull-down resistor separating the two power rails, and we're going to be measuring the voltage in between the middle of the two of them. So that voltage should be somewhere between 5 volts and 0 volts. This pull-up resistor is also known as RT, or the top one. The pull-down resistor is also known as RB, or the bottom one. Sometimes the pull-up one is also known as R1 and the bottom one known as R2. It depends who's writing the practicals. Okay, let's have a little look at our circuit. So I've pre-built the circuit. At the moment I have a 1K resistor as our pull-up resistor and 1K as our pull-down resistor. Sometimes it's a good idea just to check that power is getting to the circuit, and by doing this time it will allow us to see what the power supply voltage actually is. So using our voltmeter, we always connect black to 0 volts and we always connect the red to plus 5 volts when we want to measure what the power supply is. And if I turn on my power supply, we should see that the voltmeter is showing 4.8388, oh, it's fluctuating a bit, nearly 4.9 volts. What I'm going to do, I'm just going to remove that resistor very quickly. Okay, 4.96 it's settled on. So it might also be quite a good idea for you just to have a little look at the other power supplies in the workshop and see what voltage they might be showing. Okay, let's measure the voltage in between the two resistors. So I'm leaving the black lead where it is, and I'm moving the red lead to measure at that junction of the two resistors. And we can see from our voltmeter that it reads 2.480 volts. I'm going to just change the range as usual on that to 2 decimal places, and it's reading 2.48 volts. I'm going to enter that into my table. Now that is on that reading there where the pull-up resistor is 1K and the pull-down resistor is 1K, so our measured value was 2.48 volts. Next, I'm going to go back now to the top of the table where the pull-up resistor is 1K and the pull-down resistor is 100 ohms. So I'm going to remove the pull-down resistor. I'm going to replace it with a 100 ohm resistor. And we can see there that the voltage is reading 0.45 ohms, volts, sorry, 0.45. So we have the pull-up resistor is 1K and the pull-down resistor is 100 ohms, and that reads 0.45 volts. Next, I'm going to replace the 100 for a 220. Taking my measurement again, it reads 0.89 volts. 0.89 volts. Next to 470. And our meter reads 1.57 volts. 1.57 volts. Now we've already done the 1K. What I'm going to do, I'm going to work my way through. When you finish the 1Ks, which end at that point there, you're going to change the pull-up resistor to a 10K ohm resistor and then work through the pull-down resistors from 2.2K to 47K. When you've filled in those results, we can go back and analyze them. Okay, now hopefully you've done all your results. Let's have a little look at my results and see if yours were accurate to within at least probably 0.5 of mine. So we working down the list, it went 0.45, 0.89, 1.57, 2.48, 3.4, 4.09, 4.5 volts. We then moved to where we changed RT to be 10 kiloohms, and the results now go 0.89 volts, 1.58, 2.49, 3.4 and 4.08. Now hopefully you can see a little bit of a pattern there. What we're going to do, we're going to look at this column here, which is the calculated value. So in other words, what we would theoretically expect the values of the output of our circuit to be if all the conditions and tolerances were exact. Now we can use what's called the potential divider formula, and that is this one here. And it tells us that the voltage out of the circuit is equal to the value of the bottom resistor divided by the value of the top resistor plus the value of the bottom resistor, and we multiply that answer by the voltage in, which in our case we were using a 5 volt power supply. Let's have a little look at one of those examples, and I'll start with the first one that I did. In other words, it tells us that V out is equal to RB divided by RT plus RB times V in. In other words, V out in the first example was equal to the value of the bottom resistor, which was 1 kiloohm, divided by the value of the top resistor, which was 1 kiloohm, plus the value of the bottom resistor, which was 1 kiloohm, times our power supply V in, which was 5 volts. So this equals 1000 divided by 1000 plus 1000, which is 2000, times the 5 volts. In other words, that's equal to 1000 divided by 2000 is equal to 1 over 2, because we can cross all the zeros off, or it's equal to a half, times the 5 volts. In other words, the answer is equal to half of 5 volts, which should be 2.5 volts. So if we go back to our results and we look at the example where we used a 1K resistor and a 1K resistor, we made our measured value 2.48 volts. We've just calculated it that it should have been 2.5 volts. That's only 0.02 out, which is pretty accurate. Let's have a look at another example. Let's look at the example where we use the 1K and 220 ohm resistor. So in other words, where V out is equal to RB over RT plus RB multiplied by V in. So that is equal to, we're using RB as the 220 ohm resistor. RT was our 1000 ohm resistor plus RB, which is 220, multiplied by our V in, which is always going to be 5 volts in this experiment. Therefore, that's equal to 220 divided by 1220 times the 5 volts, which is equal to, now we're going to need a calculator for this. So 220 divided by 1220 is equal to, multiplied by our 5 volts, is equal to, and it gives us an answer of 0.90 volts. 0.90. So if we look at our results, here is our 1k resistor, here is our 220 ohm resistor. We made it 0.89 volts, and we've just calculated it to be 0.90 volts. So once again, we are only 0.01 of a volt out. I'll do one more example. This case, I'm going to use our example where we used a 10k pull-up resistor and a 47k pull-down resistor. So in other words, V out is equal to, we're going to be using in other words, it's the very last example, 47 kiloohms divided by RT, which was 10k, plus RB, which is 47k, times V in. That equals 47k divided by 57k times our 5 volts. So we're going to definitely need a calculator for this one. So 47k is 47 exponent 3, because that's 3 zeros, which represents the k, divided by 57 exponent 3 equals, multiplied by our 5 volts equals 4.12 volts. 4.12 volts. I'm very quickly just going to show you how to do that from the first line. In other words, 47 exponent 3 divided by, open our brackets because we're going to do this calculation 10k plus 47k, 10 exponent 3 plus 47 exponent 3, close our brackets, equals, and now we multiply it by the V in, 5 volts equals, same answer, 4.12 volts. So now if we have a look at that example, there is our 10k pull-up resistor, our 47k pull-down resistor, 4.08 we measured, and it equaled 4.12 volts was the calculated value, which again is only 0.04 of a volt away from our measured value, which is pretty accurate. Okay, complete the rest of the table. Okay, let's have a little look at our calculated values and check that they're accurate with our measured ones, and check that you've done the calculations correctly. So 0.45 volts, 0.9 volts, 1.59 volts, 2.5 volts, 3.43 volts, 4.12, 4.54, 0.9, 1.59, 2.5, 3.44, and finally 4.12 volts. Now, what do we notice about these results? Well, first of all, hopefully you will notice that when the resistors are the same, as in the case of the 1k and 1k, as in the case of the 10k and 10k, the output voltage is 2.5 volts on both occasions. In other words, it is half of the supply voltage. So if we look at our circuit, what we're saying is, if these two value resistors are identical, it doesn't matter what value they are, at the middle of them, i.e. at the output of the circuit, our voltage is going to be half of whatever our supply voltage was. So if that supply voltage was 100 volts, V out, if these two resistors were the same, would be 50 volts. It would be half the supply. However, if we take, for example, the first one, we can see that the pull-up resistor is much bigger than the pull-down resistor, and the output voltage is 0.45 volts. In other words, it's well below half. What that is telling us is, if the pull-up resistor is much bigger than the pull-down resistor, the pull-up resistor drops a lot more voltage across it than the smaller resistor at the bottom would do. So if we start with 5 volts, we're going to drop a lot of voltage across RT. In this case, we were dropping about 4.5 volts. So we drop about 4.5 volts across RT and only half a volt across RB, because our output voltage was 0.45 volts. So we're dropping that last 0.45 volts across RB and the majority of it across RT. So as we look, as RT is bigger than RB, whilst these values are going up, they are all less than half of the supply voltage. When RB becomes bigger than RT, then the output voltage becomes higher than half of the supply voltage. I hope that makes sense. Equally, here, RT, even if it is a different value than its previous value of RT, if RT is much bigger than RB, then once again our output voltage will be smaller. And as RT remains the same and RB becomes much bigger than RT, then the output voltage will increase well above half the supply. In other words, it will be getting up to the supply voltage. If we were to apply the logic that any voltage above 2.5 volts is called a high and any voltage below 2.5 volts is called a low, if the pull-up resistor in a voltage divider has a higher resistance than the pull-down resistor, the output voltage is going to be a low. In other words, it will be less than 2.5. If the pull-down resistor in a voltage divider has a higher resistance than the pull-up resistor, then the output voltage will be high. And when both resistors are of the same value, the output voltage is half B in, or the supply voltage. This is the end of the third tutorial.